Hi everyone, and welcome back to the Practice IB. In this lesson, we are looking at topic A1.3, operating systems and control systems. Now you use an operating system every single day, Windows, macOS, Android, and iOS. But you have probably never stopped to ask what it actually does. So that's exactly where we will start, completely from zero, no prior knowledge needed. Here is the big picture. A computer is just a pile of hardware. A processor, some memory, a screen, a keyboard. On its own, that hardware doesn't know how to do anything useful. The operating system is the clever piece of software that takes control of all the hardware and turns it into something you can actually use. It is like an invisible manager working behind the scenes every second your device is on. In the first half of this lesson, we will learn what the operating system is and the jobs it does, managing programs, memory, files, and so on. Then we will look at how it shares the processor between programs and how the devices grab its attention. And in the second half, which is for our higher level students, we will explore control systems, the feedback loops that run things like self-driving cars and thermostats. This topic is assessed on paper 1, so let's get started. Let's quickly map out where we are heading so you can see how the lesson fits together. The syllabus splits this topic into 7 parts. The first 4 are for everyone, standard and higher level. We begin with the role of the operating system, why it even exists, then its functions, the actual job it performs. Then scheduling, which is how it decides which program gets to use the processor and when. And then polling versus interrupts, which are 2 different ways for advice, like your keyboard to get the processor's attention. The last 3 parts marked HL on the right are for higher level students only. Those cover multitasking and how resources get shared, the components that make up a control system, and finally real-world control systems like self-driving cars and washing machines. If you're a standard level student, you can stop after the part 4, but honestly, the control systems part is really interesting, so feel free to watch anyway. Alright, let's begin with the most basic questions of all. What's an operating system? So, what is exactly is an operating system? Let's build the idea up using the diagram on the left. At the very bottom, we have the hardware, the physical parts, the processor, the memory, the storage, the devices. At the very top, we have you, the user, and the applications you run, like a web browser or a game. The problem is applications can't safely talk to raw hardware directly. It would be a chaos if every app tried to control the memory and disk by itself. So the operating system sits in the middle as a layer between the two. Here is the formal definition of an operating system. An operating system is the software that acts as an interface between the user, the applications, and the hardware. It manages the computer's resources and provides services so the programs can run. Now, the single most important idea on this slide is this word abstraction. Abstraction means hiding complicated details behind something simpler. When your app wants to save a file, it just says, in effect, please save this. And the operating system handles all the messy detail of how the disk physically stores it. The app never needs to know. A nice way to picture the operating system is an orchestra conductor. It doesn't play any instrument itself, but it coordinates every musician so that what you hear is one smooth, coherent piece of music. Keep that image in mind as we go. Now let's see just how much the operating system is juggling at any moment. Think of these as all the resources it manages. First, the CPU, the processor. The operating system decides which program gets to use it and for how long. Second, memory. It hands off out of chunks of RAM to each program and takes them back when they are done. Third, storage. It organizes all your files, deciding how they are saved, read, and who's allowed to open them. Fourth, input and output. Everything coming in from your keyboard and mouse and everything going out to your screen and network. Fifth, the processes. It starts, pauses, and stops running programs. Sixth, security. Handling your logins, your permissions, and encryption. Seventh, devices. It talks to your printer, your USB sticks, your Bluetooth headphones using small pieces of software called device drivers. And eighth, power. Managing sleep mode and stretching out your battery life. That's a huge amount of work, all happening invisibly. And that leads to a really common misconception I want to be clear up right now. The operating system is not just the graphical desktop you see on screen. That colorful interface with icons and windows is only one small part. The vast majority of the operating system's work happens silently in the background where you never see it. Let's zoom in on what's probably the operating system's most important job, managing running programs. To do that, we need three terms, and the differences between the first two is a classic exam favorite. First, a program. A program is passive. It is just a set of instructions sitting on your desk, doing nothing, like a recipe in a closed cookbook. Now, a process. A process is that program actually running. It is the active, living version, with its own slice of memory and its own turn on the processor. So the recipe is the program, you actually cooking the dish is the process. The third term is thread. A thread is the smallest unit that the operating system can schedule to run. One process can contain several threads, which share the same memory but can run at the same time on a different processor cores. That's how an app can download a file while still letting you scroll without freezing. Now look at the bottom of the slide, the 5 states a process moves through during its life. It starts in new while it's being created. Then it moves to ready, where it is waiting for its turn on the processor. When it gets that turn, it is running, actively executing. If it has to wait for something like data from the disk or input from you, it becomes blocked. And when it's all finished, it is terminated and cleaned up. One subtle but important point examiners love: when a blocked process gets what it was waiting for, it goes back to ready, not straight to running. It has to queue up for the processor again. We have covered the processor, so now let's quickly tour the other core functions of the operating system. First, memory management. The operating system uses techniques called paging, segmentation, and virtual memory. We will meet those properly later. To give each program its own safe private area of memory, so one program can't accidentally trample on another's data. Second, file systems. A file system is the set of rules deciding how data is named, organized, and stored on the disk. You will see different ones on different systems: NTFS on Windows, ext4 on Linux, APFS on macOS. Third, device management. Those device drivers we mentioned translate the operating system's general commands into exact electrical signals each specific piece of hardware understands. Fourth, security. A common way to remember the goals of security is this CIA triad. That's confidentiality, keeping data private; integrity, keeping it correct; and availability, keeping it accessible. The operating system protects these using logins, permissions, and encryption. Fifth, virtualization. A special layer of software called a hypervisor can run several complete virtual machines on one physical computer, each isolated from the others. That's the technology behind a lot of cloud computing. And sixth, networking and graphical interface. Running the internet protocols and drawing the windows and buttons you click on, so the operating system really is a master of all trades. Now we get one of the most important ideas in this topic: scheduling. Here's the core problem. A single processor core can only actually run one processor at a time, but you have got dozens of programs seemingly running at once. Your browser, your music, your messages. So how? The answer is that the operating system switches between them incredibly fast, giving each a tiny turn so quickly that it looks simultaneous to you. The part of the operating system that decides whose turn the next is called the scheduler. A good scheduler tries to balance several goals at once, listed on the right. Throughput, getting as many processes finished as possible. Turnaround time, the total time from when a process arrives on when it finishes. Waiting time, how long it sits in the queue doing nothing. CPU utilization, keeping the processor busy rather than idle. And fairness, making sure every process gets a reasonable turn. Now, here's a key term, context switching. Every time the operating system switches from one processor to another, it has to save the state of the current process. Things like the values in the registers and its place in memory, into a structure called the process table. Then it loads the saved states of the next process so it can carry on exactly where it left off. This happens in microseconds. But in this matters, it isn't free. Each switch costs a little bit of time, and that cost will become important on the next slide. For the exam, remember both halves, it saves state and it loads state. You need both for full marks. So how does the scheduler actually decide who is next? There are 4 main algorithms, so you need to know. And the key thing is that each one makes a different trade-off. First come, first served, or FCFS. Exactly what it sounds like. Processes run in the order they arrive, and once a process starts, it runs all the way to completion. The word for that is non-preemptive, meaning it can't be interrupted. It is simple and predictable, but it suffers from the convoy effect. If a long process arrives first, all the quick little processors get stuck waiting behind it, like being stuck behind the slow lorry on one-lane road. Second, round robin. Here each process gets a fixed small time slice called a quantum. When its quantum runs out, it goes to the back of the queue and the next process gets a turn. This is preemptive. Process can be paused. It is wonderfully fair and responsive, but all that switching back and forth creates context switching overhead, and choosing the right quantum size is tricky. Third, priority scheduling. Each process is given a priority and the processor always serves the highest priority one first. Great for important time-critical tasks, but it has a danger called starvation, where a low-priority process might never get a turn at all. A fix called aging gradually raises a waiting process priority so it eventually runs. Fourth, the multi-level queue. Here there are several separate queues for different types of process. System tasks versus user tasks, each with its own rules. It handles mixed workloads well, but it's complex, and low priority queues can still be starved. Let's make scheduling concrete with a workout example, because seeing it really helps. Imagine 3 processors that all arrive at the same time. P1 is long, it needs 6 milliseconds of processor time. P2 is medium, 3 milliseconds, and P3 is tiny, just 1 milliseconds. Look at the top bar, which shows FCFS, first come, first served. P1 arrived first, so it ran first, all 6 milliseconds of it. Only then does P2 run, and finally little P3. Now think about the waiting times. P1 waited 0, P2 waited 6 milliseconds for P1 to finish, and P3 waited 9. The average wait is 0 plus 6 plus 9, divided by 3, which is 5 milliseconds. Poor little P3 waited 9 milliseconds for 1 millisecond of work. That is the convoy effect in action. Now look at the bottom bar, round robin, with a quantum of 2 milliseconds. Each process gets just 2 milliseconds before it has to hand over. So P1 runs 2, then P2 runs 2, then P3 finishes its single milliseconds. And notice P3 is done really quickly now. Then we cycle back for the leftovers of P1 and P2. P3 finished far sooner, so the system feels much more responsive. But count the bars. There are more switches, and each one carries that overhead we talk about. And that's the lesson at the bottom. Neither algorithm is simply best. FCFS is a simpler with fewer switches, but short jobs suffer. Round robin is fair and responsive, but switching costs add up. And the right choice always depends on what you are trying to achieve. Now, a different question. Your device's keyboard, mouse, network card sometimes need the processor's attention. How did I get it? There are two approaches, and we will compare them. The first is polling. With polling, the processor repeatedly goes around asking each device, do you need anything yet? Do you need anything yet? Over and over again in a constant loop. Think of it like standing at the oven and checking every single minute to see if your dinner is ready or not. The good news, it is simple to build, the timing is predictable, and it's perfectly fine for events that happen regularly. The bad news, the processors waste loads of effort checking when, most of the time, nothing has happened. And all that checking drains a battery quickly. The second approach is interrupts. With interrupts, the device stays quiet and only sends a signal, an interrupt, when it actually needs something. When that signal arrives, the processor pauses what it's doing, runs a small piece of code called an interrupt service routine to deal with the device, and then goes back to what it was doing before. This is like setting a kitchen timer. You walk away and get on other things, and you only come back when it beeps. The advantage is the processor responds instantly and can even go to sleep between events to save power. The downside is there is a little overhead each time it saves and restores its place, and interrupts can be abused. An attacker could flood the processor with fake interrupts in a denial of service attack. So, which should you choose, polling or interrupts? The exam wants you to evaluate this properly, and the cleanest way is to walk through these 6 factors, which is exactly how the mark scheme is structured. So let's go across the table. The first one is the event frequency. If events are rare or happen at regular known times, polling is fine. If they are frequent, interrupts win. The second, CPU overhead. Polling wastes cycles checking, interrupts spends their effort saving and restoring state instead. Third one is the power source. This is a big one. Polling keeps the processor constantly busy and drains the battery, whereas interrupts let it sleep between events, which is why battery-powered devices love interrupts. Fourth one is the predictability. If events come at known, regular intervals, polling works. If they are unpredictable, interrupts handle them better. The fifth one is the latency, which means delay. Polling has variable delay depending on where you are in the checking cycle, while interrupts give a low controlled response time. And the last one is the security. Polling might miss things if it checks too slowly, while interrupts can be flooded in an attack. Down at the bottom, here is the real-world reality. Your keyboard, mouse, network card, and disk drive all use interrupts because you want them to respond the instant something happens without wasting the processor. For the exam, if you ask to evaluate, structure your answer around these 6 factors and you will capture all the marks. This section is for higher level students. Standard level, you can skip ahead to the recap. We are going deeper into how the operating system juggles many processes at once, called multitasking, and shares out limited resources. Look at the memory techniques on the left. Paging splits memory into fixed size of blocks called pages. Segmentation splits it into variable size, logical pieces, like separate sections for code and data. And virtual memory is a clever trick that uses some of your slow disk storage to pretend you have more RAM than you really do. A piece of hardware called the MMU, the Memory Management Unit, maps these virtual addresses to the real physical ones. On the right are the scheduling challenges. Preemptation is pausing a running process to let more important one go first. Starvation, which we met earlier, is when a low priority process never gets a turn, and aging is the fix. And trashing is when you have so little RAM that the system spends all its time frantically swapping pages between memory and disk, and almost no time doing real work. Now the big one at the bottom, deadlock. Deadlock is when 2 or more processes each get stuck waiting forever for a resource that the other one is holding. Picture it. Process P1 holds resource R1 and needs R2. Process P2 holds R2 and needs R1. Neither can move. That's called circular wait, and the whole system grinds to a halt. The exam phrase you must use is circular wait, and be careful, deadlock is different from starvation. In starvation, a process might still eventually run. In deadlock, nothing can ever make progress. This section is also for higher level students. We are now switching topics completely, from operating system to control system. A control system is a device or a set of devices that manages or regulates the behavior of something in the physical world. And the basic structure is beautifully simple. It follows a pattern called the IPO model. Shown across the top, I is for input. Sensors gather data about the world, like the current temperature. P is for process. A controller takes that data and decides what to do. And O is for output. Actuators carry out the decision, physically doing something like turning on the heater. But here's the part that makes the control system really clever: feedback. Shown by the orange arrow looping back. Feedback means the output is measured and fed back into the system, so it can adjust what it does next. This gives us two types, shown at the bottom. An open loop system has no feedback. It is just blindly follows the fixed plan. A microwave is an open loop. You set it for 2 minutes and it runs for 2 minutes whether or not the food is actually hot. A closed loop system does use feedback. It constantly checks the result and corrects itself. A thermostat is closed loop. It keeps measuring the temperature and switches the heating on or off to hold the target. Closed loop is more accurate because it can respond to what's actually happening. For the exam, whenever you describe a control system, always identify all four parts: input, process, output, and crucially, feedback. Forgetting feedback is the classical dropped marked here. Still on the higher level topic, let's name the 5 building blocks that make up a control system, because the exam will expect you to use the proper terms. First, the sensor. A sensor measures a physical quantity, temperature, light, pressure, motion, and turns it into a signal the system can use. For example, a thermocouple measuring the heat inside a furnace. Second, the controller. The controller is the brain. It takes the sensor data and decides what to do. A common real example is a PLC, a programmable logical controller, running machinery on a factory assembly line. Third, the actuator. The actuator is the muscle. It carries out the controller's command in the physical world. For instance, a solenoid valve that opens to let the water flow. Fourth, and this one is often misunderstood, the transducer. A transducer converts one form of energy into another, and importantly, it can work in both directions. That's why it has its own category, distinct from sensors and actuators. An example is a piezoelectric pressure sensor that turns physical pressure into electrical signal. Fifth, the control algorithm. This is the logic or mathematical formula the controller uses to decide its output. A famous one is PID control. Use it in home heating with adjust based on the error, how long the error has lasted, and how fast it's changing. Note the warning at the bottom: don't lump a transducer in with sensors or actuators. The fact that it converts energy in both directions is exactly what makes it special. This is the last higher level section, and this is the fun one. Control systems are genuinely everywhere once you start looking. The key thing to notice is that every single example follows the same pattern we just learned. Sensors feed the controller, which drives actuator in a feedback loop. Let's go through them. An autonomous vehicle senses with LiDAR, cameras, radar, and motion sensors called IMUs. Its controller runs path planning algorithms, and its actuators are the steering, throttle, and braking. A smart thermostat senses with a digital thermistor, decides with simple on-off or PID logic, and acts through the relay to the furnace. An automatic elevator senses the floor and call buttons, runs a routing algorithm to minimize your weight, and drives motors to move it. A washing machine senses the load weight, water level, and even how dirty the water is. uses fuzzy logic to decide to wash, and acts through valves and the drum motor. Traffic signal senses vehicles with inductive loops and cameras, run adaptive algorithms, and switch the lights. And a home security system senses with motion detectors and door contacts, decides with its control panel, and triggers sirens, smart locks, and alerts. Notice the exam tip hiding in all of it is. Always name the specific sensor. Say inductive loop detector, not just a sensor. That precision is what earns higher level marks. Before we wrap up, let's go over the traps that quietly cost students marks. Knowing this is genuinely worth as much as knowing the content. 1. The operating system is not just the graphical interface you see, the desktop is a tiny part, and most of the operating system runs invisibly. 2. A process is not the same as a program. A program is a passive instructions. A process is that program actively running. 3. Virtual memory is not the same as RAM. It borrows slow disk storage to extend memory, so it's much slower than the real RAM. 4. Interrupts do not always beat polling. For rare, predictable events on a mains-powered machine, simple polling can be perfectly adequate. 5. Deadlock is not just one process waiting. It specifically requires a circular wait between two or more processes, each holding what it other needs. And 6. Open loop doesn't mean broken. It simply means there is no feedback, and plenty of systems are designed that way on purpose, like that microwave. Here's my advice. In the last minute of any exam questions, run quickly through this checklist. Most marks lost on this topic aren't from not understanding. They are from these exact sleeps made under the time pressure. A few seconds of checking can rescue several marks. Let's finish the teaching with a screen you can use for revision. So pause here and screenshot it. On the left are the habits that actually score marks. For any scheduling question, always discuss both fairness and efficiency. Questions usually award marks for both. For round robin, specifically always mention the quantum and the context switching overhead. For polling versus interrupts, structure your answers around those 6 factors. For control systems, always name input, process, output, and feedback. All 4. For deadlock, use the word circular. For context switching, say both save state and load state. And for higher level applications, name the specific sensors. On the right are the command terms because what the question asks you to do matters as much as the content. Describe means just state the key features. Compare means give both similarities or differences. Both sides are required. Explain means state the feature and give the reasons or mechanism using words like because and therefore. And evaluate means weigh up the pros and cons and then reach a judgment. A conclusion is essential. Reading the command term carefully and answering exactly what it asks is one of the easiest ways to lift your marks across the whole paper. And that's the whole topic. Really well done for getting through it. Let's recap the 5 big ideas to take away. 1. The operating system is the manager sitting between you and hardware, and it hides all the complexity through the abstraction. 2. Its core functions include managing processes, memory, files, devices, security, and networking. 3. Scheduling shares out the processor's time and the 4 algorithms, FCS, round robin, priority, and multi-level queue, each trade-off fairness against efficiency. 4. Interrupts let a device signal the processor instantly while polling repeatedly checks. And you choose between them based on the event frequency, power, and latency. And 5. For our higher level students, control systems use sensors, a controller, and actuators working in a feedback loop, where closed loop self-corrects and open loop doesn't. If these lessons help you, there's a free worksheet for this exact topic linked down in the description. So go and test yourself. And for more practice questions and full walkthrough, head over to the Practise IB. If you are studying for IB Computer Science since 2027, hit subscribe so you don't miss the next topic. Thank you so much for watching. I will see you in the next lesson.